Hello. We will continue our discussion on direct current circuits by discussing a very important law that will help us to solve network of circuits. Now, what is the meaning of solving network of circuits? A network contains several resistors connected in many combinations. And if you want to find the current and potential difference on each of them, we need to use a special law, and that is Kirchoff's laws. There are two statements for Kirchoff's laws. Now, Kirchoff's laws are applied for a network of circuits, and they are stated as follows. There are two statements. The first statement is the algebraic sum of currents meeting at a junction is 0. The second statement is in any closed circuit loop. So the second law is applicable only to a closed loop of circuit. In any closed loop circuit, the algebraic sum of the potential drop is 0. First of all, you need to understand the meaning of algebraic sum. I will explain that by taking the first statement. The first statement of Kirchoff's laws says the algebraic sum of currents meeting at a junction is 0. Now watch here, A is a junction. The current reaching that junction is I1, and I2 and I3 are leaving that junction. Now when you talk about algebraic sum, you need to assign these values their appropriate sign, positive or negative. A current reaching a junction is positive, then the current leaving that junction will be negative. In the figure, I1 is the current that reaches the junction A, and I2 and I3 are leaving it. So assign them your appropriate signs. What does that mean? The current reaching a point is positive, then the current leaving will be negative. So let's apply the first law of Kirchoff to the junction A. What does it tell you? It tells me I1 minus I2 minus I3 equal to 0. That is the algebraic sum of those three currents. I1 minus I2 minus I3 equal to 0. Algebraic sum of currents meeting at a junction is 0. The second law is applicable only for closed circuit loops. I want you to listen to that carefully. I'm going to give you the statement and I'm going to explain it. I gave you the statement. Well, here is a network of circuits. Now, there is a cell of 6 volt EMF, and this resistor is 2 ohm, there is a 5 ohm and a 4 ohm. Now in the figure, A, B, E, F, A is a closed loop. Watch that again. A, B, E, F, A. I want you to watch and listen carefully how I explain the second law of Kirchoff. So second law is applied only to a closed loop. Now tell me how many closed loops can be found in this circuit. A, B, E, F, A is a closed loop. Now B, C, D, E, B. B, C, D, E, B is a closed loop. Now I want you to watch the order in which I go. Watch the direction in which my pointer moves when I name the loop. B, C, D, E, B. Remember, that loop is not the same as B, E, D, C, B. Now when you read it the opposite direction, the loop is traced out in the opposite direction. Now here we are going to talk about algebraic sum. Therefore the sign is very important. In other words, the direction in which I trace out the loop is important. You see, A, B, E, F, A is not the same as A, F, E, B, A. One is opposite of the other. In other words, if A, B, E, F, A is positive, then A, F, E, B, A is negative. Okay. Another closed loop is A, C, D, F, A is another closed loop. So we have identified 3 closed loops in this network of circuits. So the second law is applicable to all these closed loops. What does the second law say? The algebraic sum of the potential drop in a closed loop is 0. So if you take a closed loop A, B, E, F, A, now how many things are there in that loop? There is a 5 ohm resistor, there is a cell, and a 2 ohm resistor. Those are the components in that closed loop. If you now find the potential drop across each using the sign, you got to assign positive or negative. I'll be telling you that in a minute. If you now add the potential drop across the 5 ohm to the potential drop across the cell to the potential drop across the 2 ohm in this closed loop, the law says that must be equal to 0. That is the second law. The direction of a closed loop can either be clockwise or counterclockwise. That's what I have been showing you. What's this again? A, B, E, F, A. Tell me, is that clockwise or counterclockwise? Now, in what direction is my pointer tracing? Now, this is counterclockwise, opposite to the direction of the clock. Whereas A, F, E, A, B, E, B, A is clockwise. So the direction of a closed loop can be traced out either counterclockwise or clockwise. Alright. The direction of a closed loop can either be clockwise or counterclockwise. The loop A, B, E, F, A, B, E, F, A is counterclockwise, and the currents in the resistors in the loop are also in the same direction. Now, this is what I want you to watch carefully. Look at the way I'm tracing out the loop. A, B, E, F, A. What's the direction of the current? Is in the direction of I2 the same as the direction of the loop? Very well. You see? So, when you take the loop A, B, E, F, A, the direction of tracing the loop and the direction of current I2 and the direction of current I1 are both the same. Okay, but if you trace out the loop in a clockwise way, A, F, E, B, A, it means the current is now opposite to the direction in which I trace. So the direction of the current and the direction of the loop, you need to clearly understand what that means. So I have shown here, this means I traced out the loop this way. That's what this actually means. I traced it out this way, counterclockwise. So the closed loop A, B, E, F, A is counterclockwise, and the current in that loop, I2 flows in the same direction, I1 also flows in the same direction. Now the loop BCDEB, BCDEB is also a counterclockwise loop, but look at the current. The current I3 is in the same direction, but the current I2 is in the opposite direction of the loop. Is that right? Yes. So BCDEB is counterclockwise, and the current is clockwise. The current is clockwise in the 5 ohm and counterclockwise in the 4 ohm. The currents are in the opposite directions. Alright. In applying the second law to a closed circuit, we will define a loop, either a clockwise or a counterclockwise, for the circuit, and use the convention described in the next slide. And I want you to watch that convention very carefully and understand it. Alright. Convention is this. If the current in a resistor is in the same direction as the direction of the loop, then the potential drop across the resistor is positive. For example, if you now use the loop A, B, E, F, A. Now, the current in 5 ohm I2 is in the same direction. If the current in a resistor is in the same direction as the loop, then the potential drop across that resistor will be considered positive. Remember, we are looking for algebraic sum. That means some quantities will be negative, some will be positive. So we are now identifying what are the ones that are positive, what are the ones that are negative. So watch again. If the direction of current in a resistor is the same as the direction of the loop, then the potential drop across that resistor is positive. Now tell me, if you look at the loop BCDEB, tell me, is the potential drop across the 5 ohm positive or negative for that loop? The loop is traced out counterclockwise, BCDEB, and the current in the 5 ohm is opposite to that. It means the potential drop across that resistor is negative. So if the current is opposite to the direction of the loop, the potential drop across the resistor will be negative. So watch this again. In a loop BCDEB, the potential drop across the 4 ohm is positive. Why? Because the current flows in the same direction as the direction of tracing the loop. But the potential drop across the 5 ohm is negative because the direction of the loop, what's my pointer going? That's the direction of the loop, and the direction of the current I2 is opposite. So the potential drop across the 5 ohm is negative. You've got to understand that very well. When does a potential drop become positive, and when does it become negative? Now, what is the potential drop across a resistor? How do you find the potential drop across a resistor? V equal to Ri. Potential drop across a resistor is resistance multiplied by the current. And this quantity can have a positive value or negative value depending on the direction of the current and the direction of the loop that is traced out. Alright, now we talked about the potential drop across resistors. Now, if there are cells in the circuit, batteries in the circuit, there is a potential drop across the battery as well. How do we assign a positive or negative sign for that? Now watch this. If the loop is traced from positive to negative through the cell, the potential drop across the cell is positive. For example, if I trace out this loop A, F, you look at that. Look at the direction in which the loop is coming. is coming from the positive and tracing out the loop for the cell from the positive to the negative. You see that? So the direction of the loop is traced out from positive to negative. Then the potential drop across the cell will be positive. On the other hand, if you trace out the loop for A, B, E, F, A, what is the direction in which the loop is traced out in the cell? It goes from negative to positive. Then the potential drop across the cell will be negative. So if the loop is traced from negative to positive, if the loop is traced out from negative to positive, then the potential drop across the cell will be negative. So these are the rules for determining the signs. You need to understand that very well. And once you know this, we can now go and do our problem. And the potential drop across the cell is its EMF. Okay, let's practice this with an example. Now, in the loop A, B, E, F, A, the potential drop across the 2 ohm resistor, look at this, A, B, E, F, A, the loop is traced out in the same direction as the current. So the potential in the 2 ohm, the potential drop in the 2 ohm resistor is 2I1. Potential drop is Ri, resistance times the current, is 2I1 is the potential drop across the 2 ohm. That is positive because the direction in which the loop is traced is the same as the direction of the current. The potential drop across the 5 ohm resistor, what is the potential drop across the 5 ohm resistor? Will be 5 times I2, the resistance times the current. Will that be positive or negative? It is positive because the direction of the current and the direction of the loop are the same. Alright, tell me, what is the potential drop across the cell? You see, the loop is traced out now, A, B, E, F. That means you're going through the cell, which direction? From negative to positive. That means when the loop is traced out through the cell, from negative to positive, the potential drop across the cell will be negative. So potential drop across the cell now is negative 6 volt. Alright, apply the second law to this closed loop and write down an equation. What does the equation then tell you? The algebraic sum of the potential drop of all these things in that closed loop will be 0, means 2I1 plus 5I2 minus 6 equal to 0. Now, similarly, let's go and look at the loop B, C, D, E, B. In the loop B, C, B, E, D, the potential drop across the 4 ohm resistor. The potential drop across the 4 ohm resistor is 4 ohm times I3. Look at that. I3 is the current that flows in the 4 ohm. It's 4 times I3. Is that positive or negative? The direction of the current is the same as the direction of tracing the loop, so that is positive. How about the potential drop across the 5 ohm resistor? The potential drop across the 5 ohm resistor is 5 times I2, but the current is traced out in the opposite direction than the loop. Now what's it again? The loop goes like this, B, C, D, E, B, like that, and the current in the 5 ohm goes in the opposite direction. Therefore the potential drop in the 5 ohm is negative 5 I2. That's the way you calculate the potential drop. Now, we can find the values of I1, I2, I3 by setting up equations using the 2 laws of Kirchoff. And we're going to do that on the next slide. Let's apply the first law to junction B. Can you apply the first law to junction B? What does the first law say? The first law says the algebraic sum of currents meeting at a junction is 0. The current reaching the junction is positive. The current leaving are negative. We have I1 minus I2 minus I3 equal to 0. We got one equation and 3 variables. That means we need 2 more equations. Alright, to produce 2 more equations, we're going to go and choose closed loops where we can apply the second law. Let's choose the closed loop A, B, E, F, A, where we found that the potential drop across the 5 ohm is, the potential drop across the 2 ohm is 2I1, that is positive. The potential drop across the 5 ohm is 5I2, that also is positive. Why? Because the current I2 and the current I1 are in the same direction as the direction of tracing of the loop. So the potential drop across the 2 ohm, that is 2I1, and the potential drop across the 5 ohm, that is 5I2, both are positive, and the potential drop across the cell is negative because the loop is traced out from negative to positive. So applying the second law to the closed loop ABEFA gives me 2I1 plus 5I2 minus 6 equal to 0. And that is our equation 2. And look at the way I'm writing it. I'm leaving the variables on one side, taking the constant to the other. I get 2I1 plus 5I2 equal to 6. Alright, we still need one more equation. What do? Well, we apply that second law to another closed loop, which is B, C, D, E, B. Alright, can you do that on your own? Can you apply the second law to B, C, D, E, B and write down an equation? The potential drop in the 4 ohm resistor is 4I3, that is positive. And the potential drop in the 5 ohm resistor is 5I2, that is negative, because the current I2 is flowing opposite to the direction of the loop. So we get negative 5I2 plus 4I3 equal to 0. We got now 3 equations. Now the task is to solve these 3 equations to find the values of I1, I2 and I3. And actually, this can be solved on TI-83 or TI-84 or TI-89 or any graphing calculator or TI-86. I'm going to show you a method to solve those equations. In order to solve them like using the calculator, you need to write them, organize them. Now look at the way I'm going to organize. I'm going to write the first equation, 1I1 minus 1I2 minus 1I3 equal to 0. Now those are the coefficients of the variables. You see that? AX plus BY plus C equal to D. These are the coefficients. I have identified them using red colors. Now how do we write this equation in the same form? Now when you write these equations, I want you to write each equation by aligning I1, I2 and I3. That means when you write the second equation, the term in I1 must be below I1, the term in I2 must be below I2, and the term in I3, there is no I3 in the second equation. So, look at the way I wrote it. 2I1 plus 5I2 plus 0I3 equal to 6. So that I can identify the coefficients of each of the variables. Alright? Okay, in that case, how will you write the third equation in that form? There, I1 is missing, so that will be 0I1 minus 5i2 plus 4i3 equal to 0. Now, in order to solve an equation like this, after writing them like this, you need to organize the three equations in the way I have shown it to you. And now, you got to go to the calculator and make a matrix of these coefficients. Now, do you know how to make a matrix? I'm going to show you how to make a matrix on your calculator. Alright? Now, I have blocked the equations, so you now need to keep those equations with you. I'm going to read the equations one more time. You cannot see it on the screen. It is 1i1 minus 1i2 minus 1i3 equal to 0. 2i1 plus 5i2 plus 0i3 equal to 6. 0i1 minus 5i2 plus 4i3 equal to 0. What you're going to do is you're going to construct a coefficient matrix. Using the coefficients of the equations on the left side, construct a matrix called A, and then construct a matrix of the constant numbers on the right called B. I'm going to show you how to construct a matrix now. Follow these keystrokes. I will give you these keystrokes on the screen as soon as I finish this. Press second X inverse gives you this menu here. What you need to do is use the edit. So go 2 steps to the right and you're going to use matrix A, which is actually selected there. So enter, and we're going to construct a 3 by 3 matrix. So type in 3, enter 3. So when you type in 3, enter 3, the calculator constructs a 3 by 3 matrix for you. And what you need to do is write down the coefficients on the left of the first equation. You have a positive 1, enter, and negative 1, enter, and negative 1, enter. Now you have the 3 coefficients of the first equation. Now remember, a negative sign is obtained on the calculator. The bottom, the negative sign inside the parenthesis is used. Now the second equation, that's a 2, enter, 5, enter, 0, enter. Now I have finished my second equation, 2i1 plus 5i2 plus 0i3. We go to the third equation, 0, enter, negative 5, enter, 4, enter. There you've got the coefficient matrix, which is a 3 by 3 matrix. Now, we need to now go and make another matrix, which is going to be a 3 by 1. Is that right? Rows and columns. There are 3 rows and 1 column for the right matrix. So press again, second X inverse. Go to edit. Now this time we're going to make a matrix B. So down arrow and enter. Matrix B is going to be a 3 by 1. So 3, enter, 1, enter. It's a 3 by 1 matrix. What are the values of that matrix? It will be 0, 6, and 0. And we have 2 matrices A and B. What all we need to do is we go and obtain A inverse B. So we quit the screen and we go to the matrix and pick our matrix A. Now go to second X inverse, go to and pick the matrix A, enter. So that writes matrix A, and now type X inverse, that is the inverse of matrix A, and multiply that by matrix B. How do you pick matrix B? second x inverse, go down and pick matrix B. And now you enter. These are the values of I1, I2, I3. It tells me your I1 equal to 1.421. I2, there you got, I1 equal to 1.421. I2 equal to 0.632. And I3 equal to 0.789. You got the values of I1, I2, and I3. And you should be able to now solve any equations. If you have 5 variables and 5 equations, you can solve it in the same way. Any number of equations can be solved using this method. Alright, let me take it away and let's continue. So to solve these equations on your calculator, we construct a coefficient matrix A and a matrix B, which is a column matrix, as follows. I've given you the steps there. Alright. I want you to print out the PowerPoint and follow these steps if you haven't been able to catch up with me. Alright? Okay. Now follow these steps. I've given you step by step on what to do in solving these equations. You can actually pause this screen and do this on your own. So I1 equal to 1.42 ampere, I2 equal to 0.63 ampere, and I3 equal to 0.79 ampere are the values of I1, I2, and I3. That's a very neat way to solve the problem. Alright? Let's go and do another problem. In the circuit shown, the ammeter reads a current 2 ampere. The ammeter reads a current 2 ampere. Find the current in the 7 ohm, in the 2 ohm, and the EMF E of the cells. We need to find the current in the 7 ohm, the 2 ohm, and the EMF E of this cell. Okay, what we first need to do is, we need to say, what direction is the current flowing? Now, remember that current always starts from the positive of a battery and ends in the negative. So, let's say that this battery sends a current this direction. Watch the direction I'm tracing. Alright, it comes here, and this battery also sends a current in that direction, which comes to that junction, and they both come together and go through the 5 ohm through the ammeter, and they come here and split 2 ways. Well, is that a good assumption? It really doesn't matter. Even if you make a mistake, the method of the problem will correct you, because we are using algebraic sum. Alright? So, let's try first of all, let's give names to these junctions. Let that be A, that B, that C, that is D, E, and F. These names are important for us to trace out our loops. Okay, let I1 is the current in 7 ohm, I2 is the current in the 2 ohm, and I3 is the current in the 5 ohm. Alright, let's trace out that current. Let I1 be the current in the 7 ohm. This battery sends out a current I1 in the 7 ohm. And this battery sends out a current I2 in the 2 ohm. And I1 and I2 will come meet at A, will become I3, that will go through the 5 ohm. That's what we have chosen to do. Alright, once this is done, our task is now much simpler. First of all, we can use the first law of Kirchoff for junction A and write an equation. Can you write an equation using the Kirchoff's first law applied to junction A? I1 reaches A, I2 reaches A, I3 leaves A. So what will be the equation like? We have Well, we are told that the ammeter reads 2 ampere. What does that mean? The ammeter reads 2 ampere means the current that flows in the 5 ohm is 2 ampere. Because whatever current that flows in the 5 ohm has to go through the ammeter. That means we know the value of I3. And that makes this problem a lot simpler. So we got I3 equal to 2. So look at the equation we're going to write. I1 plus I2 minus I3 equal to 0. That is how we apply the first law in here. The algebraic sum of the currents meeting at a point is 0. Don't make a mistake there. Current reaching a point is positive and current leaving is negative. So I1 plus I2 minus I3 equal to 0. That means I1 plus I2 equal to I3 and I3 equal to 2. So we produced our first equation, I1 plus I2 equal to 2. Alright, let's now obtain the second equation by choosing, you can actually choose any of the closed loops to apply the second law. Alright, I have chosen the loop ADCBA. ADCBA, that loop. Now, it's more convenient for me because the direction of the loop and the direction of I3, the direction of the loop and the direction of I1 are the same. You see that? That means the potential drop across the 5 ohm will be positive and the potential drop across the 7 ohm will be positive. And the potential drop across the cell then will be negative because the loop ADCBA is traced out that goes inside the cell. The loop goes from negative to positive. So the potential drop across the cell in that case will be negative. Okay, look at the equation I'm writing now. 7I1 plus 5I3 minus 15 equal to 0. Because I know most of you will have trouble here. You see, the potential drop across a resistor will be positive if the direction of the current in the resistor is the same as the direction of the loop. Look at the direction of the loop. AD that way and the current I3 in the same direction. DCB, the direction of the current in the 7 ohm is the same direction. So there you have 7I1, there you are, plus 5I3 minus 15 equal to 0. But we know the value of I3. Or write it like this, 7I1 plus 5I3 equal to 15. Alright. But I3 equal to 2 ampere. You see, this question is very, very simple for you. And that means there is only one unknown there. That is 7I1 plus 5 times 2, 10 equal to 15. Or that gives me I1 equal to 0.71 ampere. So now you know I1, you know I3, we have only now I2 and E that needs to be determined. Well, there is another equation we can use. I1 plus I2 equal to, isn't that our first equation? Our first equation is I1 plus I2 equal to I3, or I1 plus I2 minus I3 equal to 0, which is the same as I1 plus I2 equal to I3, and I3 is 2 ampere. So if I1 plus I2 equal to 2 and I1 equal to 0.71 ampere, what is I2 equal to? I2 is 1.29 ampere. So now you know all the three currents, we need to find the EMF E. which means we now need to use a closed loop that contains that cell. Can you give me a closed loop and help me set up the equation there? Let's apply the second law to the closed loop circuit ADEFA. Look at that, ADEFA. Why did I choose that loop? Because that's the loop that contains the cell whose EMF we need. Alright, can you help me write the equation? ADEFA. The direction of the loop is the same as the direction of I3. The potential drop across the 5 ohm will be positive 5I3. Alright, now look at where the loop is going to come. In which direction is the loop going to be traced through the cell? From negative to positive. That means the potential drop across the cell now is negative E. And the potential drop across the 2 ohm will be 2I2. There you got 2I2 plus 5I3 minus E equal to 0 is the equation you get there. You know the values of I2 and I3, find the value of E. So I2 is 1.29, I3 is 2. That gives me E equal to 12.58 volt. Okay, that was a simpler one. Let's do another one. In the circuit shown, find A, the current in each resistor. This is the circuit. The current in each resistor, the potential difference between points A and B, and C, the power supplied by each battery. Now, what is the power supplied by a battery? The power supplied by a battery is its EMF multiplied by the current passing through it. Okay. First of all, we start giving the name. That is A, that is B. So let's say that is C, that is D, that is E, and that's F. Once you have those, we can now take closed loops and so on. But before that, we must assign the directions of current. Alright? So, this is the positive part of the cell. So let's say a current starts here, goes through 4 ohm and comes to A. A current starts from here, goes through 3 ohm and comes to A. And they both meet and go through the 6 ohm. We will assume that that is the way it is going to be. Even if we are not right, it doesn't matter. So, let I1 be the current leaving the battery on the right. So let that be I1, the current leaving the battery on the right. And let I2 be the current leaving the battery on the left. They meet at A and I3 leaves A. So I2 and I1 will come and meet at A and I3 will leave. Okay. Applying the first law for junction A gives, can you write down that equation? I1 plus I2, look at that, I1 plus I2 minus I3 equal to 0. Now let's apply the second law to the closed circuit. What's the closed circuit? A, B, D, C, A. A, B, D, C, A. Can you now write down an equation for that? Now the loop is traced out in the same direction as I3, is that right? And the same direction as I1. That means the directions of I3 and I1 are the same as the direction of the loop A, B, D, C, A. So, it will be therefore 3I1, the current in the 3 ohm is 3I1, plus 6I3, potential drop across the 3 ohm is 3I1, potential drop across the 6 ohm is 6I3, so 3I1 plus 6I3, the potential drop across the cell. You see, look at the way the loop is traced out. It goes through the cell from negative to positive. The potential drop across the cell is negative 12. 3I1 plus 6I3 minus 12 equal to 0. And writing down, taking the constant to the other side, you have 3I1 plus 6I3 equal to 12. You've got a second equation. Now produce a third equation. Which loop will you take? Let's take EABFA. Look at the way this time I chose the loop go clockwise. Now it's convenient for me because look at the way I2 and I3 are in the same direction. That means the potential drop across the 4 ohm is 4I2. I2 is the current there. And the potential drop in the 6 ohm is 6I3. And the potential drop in the cell is negative 12. And we have 4I2 plus 6I3 minus 12 equal to 0. And that gives me 4I2 plus 6I3 equal to 12. Okay. Now, write down these equations in the proper way. How? It will be 1I1 plus 1I2 minus 1I3 equal to 0. Rearrange the equation. I haven't this time put the ones, but you understand that. And the second equation is 3I1 plus 0I2. There is no I2 there, so I added 0I2. Plus 6I3 equal to 12. And 0I1 plus 4I2 plus 6I3 equal to 12. These equations are now ready for you to solve on your calculator, whatever calculator you use. So make your matrix A. It will be 1, 1, negative 1, 3, 0, 6, 0, 4, 6. That will be your 3 by 3 matrix A. And then make your 3 by 1 column matrix, 0, 12, 12. And then calculate A inverse multiplied by B. And you will get I1 equal to 0.89 ampere, I2 equal to 0.67 ampere, I3 equal to 1.56 ampere. And that is a very, very neat way to solve problems. Now remember, in a normal complicated electrical circuit, like a radio circuit or a television circuit, there are hundreds or thousands of components connected in all kinds of networks. That means you will be producing equations that containing sometimes hundreds of variables. So you need a computer program. The computer will make up these matrices quickly and solve those equations for you. Alright, we also now, part B, find the potential difference between A and B. Now what is the potential difference between A and B? The potential difference between A and B is the potential drop across the 6 ohm resistor, which is 6 times I3. So the current in the 6 ohm is 1.56 ampere. So the potential drop across that 6 ohm is 6 times I3. V equal to Ri. That is 6 ohm times 1.6 ampere. That is 9.36 volt is the potential drop across the points AB. What is the next thing that we need to find? We need to find the power supplied by the batteries. Now, power supplied by a battery is its EMF multiplied by the current. Well, we know the EMF of the first cell. We know the current that flows through it, that's I2. We know the EMF of the cell on the right, and we know the current that flows in it. The current in the battery on the left is I2 equal to 0.6 ampere. Therefore, power supplied by this battery is P equal to EI. That will be 12 volts multiplied by 0.67 ampere. That is 8 watts. And the current in the battery on the right side is I1. That is I1 equal to 0.89 ampere. The power supplied this battery is P equal to EI. That is 12 volts times 0.89. That is 10.7 watt. So we now obtained the power supplied by each of the batteries. Let's do quickly a final one. In the circuit shown, find the current in each resistor, the power dissipated in each resistor. Now this is the circuit. Find the current in each resistor. Let I1 be the current reaching A. Well, let I1 be the current reaching A, and I2 and I3 be leaving it. Let I2 and I3 be the current leaving it. It doesn't matter. Sometimes I2 may be that way. In such a case, we will get a negative answer for our result. So we will make a beginning like that. That means, alright, name each of these points. Apply the first law to junction A. What will the equation be? You got I1 reaching, I2 and I3 leaving. You get I1 minus I2 minus I3 equal to 0. You get your first equation. Let's apply the second law to the closed circuit ADCBA. ADCBA. I would like you to do that on your own. That will be the current and the loop are in the same direction in both cases. That will be 1 times I3. That's 1 times I3 plus 3 times I1. So that will be 3 I1 plus 1 I3 minus 5. You see, the loop is traced out from negative to positive. So 3 I1 plus I3 minus 5 equal to 0, which is 3 I1 plus I3 equal to 5 is our second equation. And now let's choose the closed loop EFCDE. EFCDE. This time I chose the outer closed loop. And now look at the way. Can you tell me what is the current in the 2O? If I2 is the current there, that's the current that passes through the cell, which will now come and pass through the 2O. So that is in the same direction as the loop. So that will be 2I2. And watch this. The loop is going in that direction. The current I3 is opposite. Alright? So look at the equation. 2I2, that is positive, minus 1I3. Why minus? Because the loop goes in the counterclockwise. Current I3 goes in the opposite direction. So that will be 2I2 minus 1I3, and the loop goes from negative to positive in the cell, minus 7 equal to 0. That is our next equation. That gives me 2I2 minus I3 equal to 7. We've got now 3 equations. You know how to organize them and solve. Those are the 3 equations. Now first of all, arrange them in the way I showed you. Well, it'll look like this. And once you have written them like this, obtain your matrix A and matrix B and calculate A inverse times B. That will give you I1, I2, I1 equal to 2 ampere, I2 equal to 3 ampere, I3 equal to negative 1 ampere. What does that tell you? It tells me that I3 is not really that way, it must be that way. In other words, a large current sent by this cell comes in, divides at B, then goes through the 1 ohm and joins here. That's what it means. I3 actually should be in the opposite direction. So it doesn't matter whether you made a mistake in assigning the direction of the current. I3 equal to -1 ampere means that the current in the 1 ohm resistor is not from A to D, but from D to A. Alright, what is the power dissipated in a resistor? The power dissipated in a resistor is the value of the resistance multiplied by the current. So P equal to Ri squared. Is that right? The power dissipated is V times I. If V equal to Ri, power dissipated is Ri squared. So let's find the power dissipated in the 3 ohm. The current in the 3 ohm is I1, which is 2 ampere. So the power dissipated is 3 times 2 squared, Ri squared, that is 12 watt. The current in the 1 ohm is 1 ampere. Now remember, as far as the power dissipated is concerned, the sign doesn't matter. So we only need the positive. It's going to be squared anyway. So the power dissipated is Ri squared, 1 times 1 squared. That is 1 watt. And the current in the 2 ohm is I2 equal to 3 ampere. Isn't it? This must be, the current in the 2 ohm is I2 equal to 3 ampere. Please make that change. Therefore, power will be, yes, I have made that change in there. 2I squared, Ri squared, 2 times 9, that is 18 watt. So the total power dissipated is, add all these, that is 31 watt, and which must be equal to the total power supplied by the 2 batteries. The power supplied by the 7 volt battery is 7 volt times I2. That will be 7 times 3, 21 watt. And the power supplied by the 5 volt battery is 5 times I1, 5 times 2, that is 10 watt. You can see 21 plus 10 is 31. The total power supplied is 31. The total power consumed is 31. The total power supplied equal to 31 watt, which is equal to the total power consumed. Alright, I think we spent a considerable amount of time in this lesson. You are now ready for your test 4. Alright, I will see you later on.